Okay, it's 4:02. Good afternoon, everyone. So last time we studied symmetric key encryption, and we left the last class at asymmetric key encryption, and we were discussing RSA, discussing why RSA works. In particular, we had two properties, right? Once you encrypt a message with a public key and the corresponding private key subsequently, you obtain the message itself. And the second property is that for anyone, for any computer of today, it should be infeasible to obtain the private key just by looking at the public key. And obviously, we also provide other properties of encryption, such as that no party should be able to compute any function of the message. That still applies. Okay, so here is where we left. I'm going to revise some of the properties we have seen. So this is the most important property we will be using today. Hello. So we also saw how a binary representation of a number can also be converted into a decimal representation, right? So when we are looking at the decimal numbers only here, they can also be applicable, the same operations can also be applicable to binary numbers. So this is how RSA protocol operates. First, to create a public and private key pair, you choose two very large prime numbers, P and Q. And these numbers are very large, 1024 bits each at least. So this number is a sufficiently large number to make this RSA scheme secure. Maybe 10 years later, we will be discussing 248-bit prime numbers. And then we compute n. N equals P times Q. So the only factors of n are P and Q. And we also set z as P minus 1 times Q minus 1. And then we also choose a number E such that E and Z have no common factors. There is no number that divides both of them other than 1. And then we also choose a D such that ED minus 1 is exactly divisible by Z. So that is ED mod Z equals 1. And from there, we have our N's, we have our N, we have our E, and we have our D, correct? So from there, we say that N and E are the public key, and N and D are the private key. And we can use them to encrypt any message we want. And the encryption is by means of exponentiating a number, the message, with E or D, depending on which key you are applying, and then taking modulo N. So if you're encrypting a message, you exponentiate it and take modulo N. This is your ciphertext. And this is why RSA is very difficult. These numbers are very large numbers, E and N. And if your message is also large, this exponentiation, called modular exponentiation, takes perhaps a few milliseconds with today's computers at least. And imagine doing this thousands of times during your communication with a web server, because you need to encrypt all your messages, right? And the decryption operation is the same, only this time we are using the public key. And if you consecutively apply the public key and private key encryption, you get the original message. And now we're going to see why that works. So the property we want to show here is that this is your ciphertext, C. When you encrypt the ciphertext with the public key, you get the original message. So C was the message encrypted with the public key. So C is the ciphertext, and you obtain C by encrypting the message with the public key. And then if you encrypt C with the private key, then you obtain the original message. And we are going to prove why that works. So I'm going to give out just a fact here from number theory. and we are not proving this. The proof of this itself takes a few pages. So here's our property which we're going to be using in addition to the earlier exponentiation property of modulo operation. And also recall that n was equal to p and q. This is how we chose our p's and q's and how we derived our n value. And this is how we have chosen the z value. So this is the property we want to prove. So C was your ciphertext, and this is how it was calculated, right? So I put it here. And now we are using this property here. This is the property you saw in the previous slides. That was, let's see, it is this property. If you are exponentiating a mod n, this is equivalent to a to the d mod n. So when I apply this property with a equals m to the e, this gives me a, m to the ed mod n. So I applied this property where a equals m to the e, and I substituted m to the e here. M to the e to the d equals m to the ed, right? And from there, we will be using this property from number theory, and we are applying it with, let's see, we are applying it with m equals x and ed equals y. So what happens then? I'm substituting m and ed values here. So on the right side of this, I would have m to the ed mod z. And I still have mod n here, right? This is exactly what that is. And remember how I have chosen z. I chose z such that ed minus 1 is exactly divisible by z. In other words, ed mod z was equal to 1. And therefore, this portion is just 1. And then I have my m mod n. Because m is a small number compared to n, it is just m. So this is why RSA works. There is an example here, so you can just try out with the exponentiation. I won't go through that. And one other important property we discussed was that it doesn't matter whether you encrypt with the private or public key first, you still get the same message when you encrypt consecutively. And here is the proof for that. So here, I'm first encrypting with the public key. I'm using E first as the exponential. And then I'm encrypting with the private key later on. I'm exponentiating with D later on. Again, we apply the exponentiation property of modulo operation we saw earlier. So this is equal to m to the ed. Well, it doesn't matter if you multiply. So you can change the order of multiplication, right? So I can change the locations of e and d here. So that gives me m to the d e mod n. And again, I apply that exponentiation property of modulo here to have it in this format, which is encrypting with the private key first and public key second. Okay, so these modulo operations and exponentiations won't be in the final exam. I'm just showing you here to give an idea of, to provide some insight as to why that works. RSA is not the only asymmetric cryptographic scheme or cryptographic system that we have today. We have others as well. But it is the most primitive one, the first one, and that is still being very widely used all around the web and all around many applications. But let's also say that, let's say you want to implement a system. Let's say you want to build applications that run on two end systems, and these applications need to communicate securely. In other words, they need to send messages with the confidentiality property. And let's say you want to use RSA for some reason. In implementing these applications, or when implementing security in these applications, you, as a programmer, you do not take exponentials of these numbers or messages, if you will. What you instead do is that there are already built-in libraries in almost all programming languages, maybe unless you use assembly language or something. There are existing libraries for all of these, and these implementations are already proven secure. They are very widely used. Most of them are open source. So you can just call the libraries, call the modules in your application program, and then implement these. So you do not, in fact, go down deep and take exponentials and modulus of these numbers and get lost somewhere. And in fact, in the practical application, it is usually not as simple as we have seen here. Maybe there are some other steps that are added later. This is the most primitive form to show why that works. All right? Any questions? Okay. And one thing we didn't discuss so far is why RSA is secure. In other words, how hard it is to determine the private key out of the public key, or any ciphertext, so to say. So let's say you know Bob's public key, which is practically the case. You always know the public key. This is publicly available, as the name implies. How hard it is to determine D, because as you recall, this is the private key, N and D pairs. So essentially, to find out the D value, one needs to factor that very large number n to its factors p and q. Remember, n was equal to pq, right? And both p and q are two arbitrarily selected prime numbers. And it is difficult for today's computer. In other words, there is no known algorithm that can factor numbers efficiently other than trying brute force. Maybe there are some methods that can make it a little bit easier, but still the complexity of that algorithm increases fast with the size of n, or with the size of p and q. So therefore, if you choose a sufficiently large p and q values, today it is 1024 bits per number, it is very difficult for today's computers, almost impossible, not impossible, but almost impossible, perhaps takes thousands of years with the best computers, to factor that large number n. But if you reveal any of these values, p or q, then it becomes very, very easy. So let's recall how these were calculated. So now, if I reveal P, N is also known, right? N is part of the public key. They can just find Q by N over P, right? So if P and Q are known, Z is also known, because Z is P minus 1 times Q minus 1. These are immediately found. And then I was choosing E, right? That has no common factors with Z. Because Z is also known, the adversary can also guess that E number. E was already in the public key. Sorry, E is already known. Let's look at D. D was the part of the private key. So Z is known, E is known, and in choosing D, the key generator has chosen a D such that ED minus 1 is exactly divisible by Z. Now, because Z is known, the adversary can just try out the values of D, and without much difficulty, today's computers can compute that a lot easier. They can guess the value of D. So you should not reveal any of these P and Q numbers or any other number that you used in generation of these public and private key pairs, other than, of course, N and E, which are the parts of the public key. Okay, again, these are just to provide insights as to how such asymmetric key crypto system can work. Because maybe it sounds intuitive to most today, but at the time it was invented, there was only symmetric key encryption. And people really thought that in order to have security, in order to provide confidentiality properties, you first need to have a secret. That was the thinking at the time. And once this RSA came out, it was revolutionary because suddenly you do not have to share a key and you do not have Diffie-Hellman key exchange. You can just encrypt your message with the public key of the receiver, and it won't be deciphered by anyone else other than the receiver. So it was quite revolutionary at the time it was invented. Okay. So we already discussed exponentiation in RSA is computationally intensive because of the modular exponentiation. And DES, so this was the symmetric encryption scheme, and also AES, they're at least 100 times, sometimes thousands of times faster than RSA. So even though we can potentially use RSA to encrypt our messages, we still prefer to share a key and encrypt the messages with our shared key if the confidentiality is the property we want to provide. Because of the simple reason of symmetric key encryption being easier and faster. And we just use RSA first to establish keys and then use symmetric key encryption. And once that session key is established, we can just use that symmetric key to send our messages, to encrypt our messages, and protect them against any eavesdropper. So maybe let me show that in practice how that protocol works. So let's say this is Alice and this is Bob, and they want to have secure communication in the sense that they want to encrypt their messages so that no eavesdropper can derive meaning out of their messages or compute any function of their messages, right? That's what we learned. So if they had a shared symmetric key, that's all fine. When sending a message, Alice will just encrypt that message with KS, the shared key. And then, Bob will just encrypt that again, or in other words, decrypt. And he will obtain M1. So this is symmetric key encryption, such as in the case of AES or DES. But now let's assume they do not share a secret. In other words, KS is not established among them. They haven't met earlier. Maybe this is the first time you are contacting a web server. Then this is how it works. So Alice has, or let's say Bob has a secret key, a public key and a private key. And I'm going to denote these by KB plus and KB minus. Okay, so this is my public key, and this is my private key. Private key is only known to Bob, and public key is known to everyone, including Alice. So now, Alice will choose a secret herself. It can be any arbitrary secret. For now, that secret is known only to Alice. Let's say, again, that is KS. And Alice then will send that KS in encrypted form after encrypting that KS with Bob's public key. So over that insecure communication channel now, KB plus of KS will be transmitted. But unless you know the private key of Bob, you cannot decipher this message. You cannot derive any meaning out of this message, correct? Only Bob can decrypt this because he has his private key. And then the Bob will do this operation. To decrypt that ciphertext into KS. Now, only Alice knows KS, and only Bob knows KS. No one else knows KS. From there on, Alice can just, or Bob can just, either of them, can exchange messages by encrypting their messages with that KS. Like so. So in practice, these shared keys are replenished after a while, and the time they are being used are usually called sessions. So throughout a session, the same shared key is used, and when the session is renewed, they establish a new key pair and so on. That is, in practice, how we do it. Yep. Any questions on this? So as we just saw, Bob and Alice they can use RSA, they can use ECDSA, any asymmetric key crypto system to exchange a shared key, to establish a shared key, and then they use that shared key to encrypt their messages from there on. Okay, so that was about encryption. And encryption is used to ensure confidentiality of the messages so that no adversary can compute any function of the plain text message. Now we are moving on to message integrity, and that is to make sure that the message is coming from the source that it is claimed to come, and that the message has not been modified in transit. So if you recall the experiment in the last class, that I asked you to write a message, and that message was modified in transit. You said someone must have swapped the message, right? So swapping is one way. I could also forge a completely new message when you don't send a message. Or I can just change your message. I can tamper with your message. I can perhaps add a few words. Or I can just add, when you say the weather is good, I can just say another words and say the weather is not good. So I can tamper with messages. I can forge new messages. And message integrity and authentication are our security tools, our mechanisms to prevent that kind of attack. So message integrity is also called message authentication. And we need two properties here. First, if Bob is receiving the message, Bob needs to ensure that the message indeed originates from Alice. Indeed, it is coming from Alice, but no one else. And that message was not tampered with on its way to Bob. So here, Alice is sending a letter to Bob. Let's see how it goes. So Bob received the message. But, there's another person here, Trudy. She can also send a letter to Bob. And Bob has two letters. And in both letters, it's saying, "Dear Bob, how are you? I'm fine. Why don't we meet tomorrow? Alice." So both letters claim that they are coming from Alice. So what should Alice do then to prove that this message is coming from Alice, but not the other message? Well, she should attach something to that message that proves that the message originated from Alice and that it has not been tampered with. So today in the physical world, we do this by, for instance, signatures, right? You attach something out of you, something that only you can generate but no one else, to your message or to the document. You sign the document, and you associate that piece of evidence with that document. So it has to include parts of the documents. In real life, we do this by signing the same document, right? So let's say I'm going to court and I want to prove that these documents are from me. I cannot just sign any random piece of paper, right? I have to sign that paper. So my proof must include some piece of me, my identity, and some piece of the thing I am signing. And now we are going to see methods to provide integrity, and one of which is also called digital signatures, an allusion to the signatures we have in real life, in physical life. But there are other methods as well, we shall see them now. Okay, so before that, we need to discuss a very important cryptographic primitive called hash functions. Maybe you have heard the name before. So hash functions can be a very large class. There are different kinds of hash functions for different purposes. The hash function we are talking about here is also called the cryptographic hash function or secure hash function. And this is only a subclass of hash functions with certain properties. But overall, hash function does this. You give a message to the hash function, message M. It can be any arbitrary message. It can be short, it can be large. And then the hash function computes a digest, which we denote by H of M. And despite the arbitrary size of the input, this output digest has a fixed size, depending on the hash function you use. So this is perhaps 128 bits or 256 bits, but for that particular hash function, it's always constant. So in practice, when you're taking hash, this is how it looks like. Let's say Bob now writes a message to Alice, a letter to Alice. So here's the array list, some messages, and then it claims it's coming from Bob. And if Bob takes the hash of this, no matter how long this message is, it will always produce a fixed length digest or hash value. Okay? And now we are going to discuss some of the, not some actually, just all of the properties of the cryptographic hash functions. How shall we do it? Okay, let's go through this slide first, and then I'm going to explain in more detail what each means. So first of all, hash function is many-to-one. It can take any arbitrary length message and output a fixed size n-bit digest. It should be one way, meaning that computing the hash should be easy, but the other way around, very difficult. The other way around meaning you cannot compute the message from its digest. And this is also known as pre-image resistance. And the collision resistance is that you cannot find two different messages with the same hash value. And also, another property is that if you change the message even if a little bit, let's say I add one letter to my message, the digest changes completely. Okay? So this is just a very fast overview. Let me go through in detail here. Okay. Let's say hash functions. So hash functions are, after all, they are functions. Okay, so we can also define them mathematically. So our first property was that they are many-to-one. Many-to-one. So for any function, we have a domain set, correct? Let's say this is our domain. And there are some elements in the domain set. And this function maps this domain set to a codomain set, or this is also called the range of the function, or codomain of the function. There are also some elements here. And we say that this function maps the elements of the domain to the range. Right? This is a definition of any function. But now the hash functions are a special kind of function. And this mapping is such that in our domain set, you can have any real number. So it maps any real number to a fixed size digest. So you can have a sequence of zeros and ones of fixed size. And k is perhaps this is 128, or this is maybe 256, or it might get larger in the future as our computers get better in computing these hashes, and as we require more security in them. So I represented the range using the binary format, but you could also represent this using maybe, let's say n is the natural numbers, by using intersection of the natural numbers and from 0 to 2 to the k. So this is all the integers from 0 to 2 to the k minus 1. So what does it imply then? So many-to-one property means that there are infinitely many elements in our domain set, correct? It can be any real number, and we know that the set of real numbers has an infinite size. But in our range, we have a limited size set, a fixed size set even. So we can only have 2 to the 256 elements in there. So that undoubtedly implies that for some of the elements in my domain, I have to map them to the same element in my range. So maybe I have to map this element and this element in my domain set to the same digest value in my range. Right? This has to happen. And therefore, we are calling this many to one. Many elements in the domain are mapped into one number, one element in the range. So this was our first property. Second is one way. One way means simply you can very easily compute the hash of a message. So given m, you can compute h of m very easily. But from h of m, you cannot get to m. This is infeasible with today's computers at least. Also, keep in mind that here, for any digest value, for any h of m, there are infinitely many m's, right? Not just one, because my domain set was much larger. So this property states that for today's computers, it has to be infeasible to find any of these m's, any of these messages that correspond to a digest value. It is not saying it is impossible to find it. It may be possible if you get lucky, but it is infeasible with today's computers. So that's simply one-way property. Now, this is not a mathematical notation or anything, but just explain the one-way property. And well, actually, this is a combination of the preimage resistance and one-way. So let's also add the preimage resistance here. So one-way means that from m to h of m, this is very easy. And preimage resistance states that from h of m to m, this is infeasible. All right. And next we have the collision resistance. So for collision resistance, again, remember that for multiple values in the domain, we might have a single element in the range set, right? And with the collision resistance, we are stating that it is infeasible to find two messages that would result in the same digest value. So it is that you cannot find M1 and M2 such that h of M1 equals h of M2. Again, we are not saying it is impossible to do so. We are not saying it is impossible to find two messages that would result in the same digest. All we are saying that it is infeasible for today's computers, perhaps takes thousands of years with the best computers today, to find M1 and M2 such that h of M1 equals h of M2. This is the collision resistance property. And one last property is, I don't have a name for that, But a small change to a message should change the hash value dramatically. So let's say this is my message. You know, the class is silent today. And I computed the hash of this. Let's say this is the hash of that same message, which gives out a digest, right? Let's say my digest consists of a lot of value, a lot of bits, a very long bit sequence of 256 bits. And now, let's say I modified this message just a little bit. So I added a period here at the end of my sentence, at the end of my message. Now, my digest dramatically changes, meaning that it should be statistically indistinguishable from any digest, and it should maintain no similarity to this earlier hash value. It should be completely different and statistically indistinguishable. That's also a very important property for secure hash functions. Any questions? Yeah. All right, can I change? Okay. So there are, again, some commonly used hash functions. MD5, it was more frequent earlier. Today, SHA-2 is the most frequently used one, or SHA-256. It's also known as SHA-256. Secure hash algorithm. The abbreviation means the secure hash algorithm. Yeah, we're not interested in how they compute the hashes, they just do. And if you're programming a security function for your application, again, you do not concern yourself with the details of hash computation. You just call the hash library or a security library such as OpenSSL library and use these functions as defined there. But I recommend you to use SHA-256 or SHA-2 because that is still considered secure, and the other algorithms such as SHA-1 and MD5 are found to have vulnerabilities. Okay, so we discussed the hash functions as a primitive, but we still don't know how they can be useful. So let's go over this example and see how hash functions can help us for providing message authentication or ensuring the integrity of messages. So let's say Alice creates a message M and computes the hash of M, digest. And then Alice sends both M and H of M to Bob. Bob receives both messages. And then Bob verifies by taking the hash of this message. So Bob computes H of M and sees if this H of M is equal to the one he received from Alice. So does that work? any flows to this? So this is simply, let me write the protocol here. Alice and Bob. Okay, so Alice created a message, and she sent the message and the hash of that message, right? And Bob took that message and compute the hash of that message here, which gave her m prime. Let's say that's any value, and then he checked if m prime is equal to n, and if that is equal, he just knows that the message comes from Alice. Is there anything wrong with this? Any ideas? Okay, so I want you to think about who else can calculate h of m. Is it only Alice who can calculate h of m? Hash functions are well-known hash functions. Maybe Alice just used SHA-256. Anyone who can just call SHA-256 libraries can compute the digest of any message. So, if I just, as the intruder here, I can just send the message n to Bob by sending that together with the hash. Let's say this is coming from me, Utku. And then Bob will take the digest of my false message n. He will obtain an m prime, and he will see it equal to my message n. So then Bob must think that I'm also Alice. So it doesn't work. And to make that work, they still need a secret. Alice and Bob must have a secret that only they know to make sure that the message in fact originated from Alice. And in practice, we solved that problem by introducing a secret very intuitively. And this is known as message authentication codes. This is also a very well-known standard in network security. So here, we assume they share a secret. We don't care how they established that secret. Maybe they met each other, maybe they used Diffie-Hellman key exchange, or maybe they used RSA prior to this protocol to establish a shared secret key. We don't care that. We just assume they have a secret key. So now Alice creates a message m and then calculates the hash like this. So this operator between m and s is the concatenation operator. So you just put them next to each other and then compute the hash. And then Alice sends both the m and the message authentication code. This is what we call the message authentication code, or MAC in short, to Bob. And then this is how Bob verifies. Well, Bob just puts the message and the secret next to each other like this. So he concatenates. He does the same operation because he also knows the shared secret key, correct? And he takes the hash of this thing. Hash functions are public. Bob can do that too. And then he sees if this is equal to the MAC Alice sent him. And if that is equal, that means the message must have come from Alice because she's the only one who knows that shared secret key, other than Bob himself, of course. Okay, so that's a very intuitive method. We are combining the secret keys with the message authentication codes. And as you notice here, there is no encryption here. Nowhere at all we have encryption. So this also shows you you can have security without encryption, and encryption and security is not the same. So let's see this block diagram. This is the description of the same thing. So on the left side, we have the sender, or Alice in our case. Alice has the secret S, and Alice created a message. So Alice took the hash of the message and S, H of M plus S, or M concatenate S, doesn't matter. And then she sent both the message and H of M concatenate S over an insecure network, such as internet. Bob received both the message and the message authentication code, H of M concatenate S. So Bob added that same shared secret to the message and computed the hash, and then he compared whether this MAC equals to the MAC he received from Alice. And if that is equal, that means the message must have come from Alice, and the message must not be tampered with on its way to Bob. Why is that? Well, because if someone changed this message, let's say Bob received M prime instead of M, that's some other message, then he will compute H of M prime plus S, right? And he will see if that is equal to H of M plus S. Right? He will see if these two are equal. And that modification can be very small. M prime can be very close to the original message. But what did we learn just now? That is, even if you make a very small change in the message, this digest would be completely different. It's statistically just a normal digest that is completely different from the first digest. So because of that, that verification on the right-hand side will return not accept, so it will not be accepted. H of M prime S is not equal to H of M concatenate S. So that means just because Alice is the only one that knows the shared secret key other than Bob, it must have come from Alice, and that the message must not have been changed in transit. So it provides us both the properties of message authentication. Any questions here? Okay, but now we need to discuss some of the problems with the symmetric key encryption here. First of all, we have to have a shared symmetric key. And to do that, there are certain methods, yes. But you still need to do those steps prior to sending any message. And also, this message authentication codes that use symmetric key are not good for, or when I say symmetric key, it can be symmetric key or shared secret. So I'm using them interchangeably, by the way. So these message authentication codes that use shared secrets are not good for the broadcast scenarios. Broadcast meaning that I am sending my message to not just Bob, but multiple parties. So if you think about why that is, again, let's go to the board. So for point-to-point communication, I just share a secret, and I send my message together with the misauthentication code. Correct? But now let's say I have multiple destinations and I'm sending the message to them too. And for them to verify that message, they also share that same secret S. Correct? I'm sending the misauthentication code that is computed with S, and in order to be able to verify this, you must possess S, that shared secret. But now the problem is that this is no longer a shared symmetric, this is no longer a key shared between two parties, just Alice and Bob, but now it is shared among a group of people or group of devices. Now the problem is any one of these devices can forge that same misauthentication code because they possess S. So, this guy can claim to this guy that the message M prime is coming from me, and he can attach the correct misauthentication code. Do you get the problem? So this is known as impersonation. Any one of the group members can impersonate the other member. So this misauthentication codes are great for point-to-point communication, but they do not really prove the identity of the sender if you are sharing that symmetric key among a group of people, a group of devices. Well, then you can think, how can we solve this problem by still using symmetric keys? Well, you can do that, but then it becomes a little bit difficult. Now I need to share pairwise symmetric keys with every one of my destinations. So I share the key S1 with the first guy, I share the key S2 with the second guy, and I share the key S3 with the third guy. And I need to possess, of course, all S1, S2, and S3 keys. So now, if I'm sending a broadcast message to all of them, I need to compute 3 misauthentication codes. M, misauthentication code computed with S1. I send this to the first guy. For the second guy, I send the misauthentication code computed with the second shared key. And for the third one, I send the misauthentication code computed with the third shared key. So I need to compute all these 3 MAC values and send these messages individually to all of my receivers. And that introduces additional work for me, right? I need to now compute 3 hashes. I need to send each of them separately rather than just sending one message. So it introduces both a computation and communication overhead. Additional tasks for me to do. Well, luckily, in such a scenario, we do not have to use symmetric key based misauthentication codes. We can use something called digital signatures, and they are not really analogous, but they are kind of similar to the signatures, the physical signatures that humans sign under the documents. So in a digital signature, the sender, in our case Bob, digitally signs the document and establishing that he is the owner or the creator of that document. And the good thing about this is that it is publicly verifiable. So now not only my destination can verify that it is coming from me, any member of the public can verify that that message is coming from me and it has not been tampered with in transit. And this is non-forgeable. So unlike the shared keys, shared key-based message authentication code. Now, my destinations cannot forge it because they do not know my private keys. This digital signatures is based on asymmetric key cryptography system, just like RSA. So this is how that works. Let's say Bob has a message M, the same message to Alice. Dear Alice, sorry I have been unable to write for so long, blah, blah, and it claims it is coming from Bob. So now Bob runs this message through an encryption algorithm, such as RSA, but this time using his private key. So remember, for confidentiality property, we were encrypting with the public key of the destination, so that our destination, but only our destination, can decipher that message. But now Bob is encrypting that message with his own private key. And because only Bob knows this private key, only Bob could have signed that message, but no one else. So Bob sends the message encrypted with the private key. Is it good? Any questions? Okay, but this is not enough. This is just our introduction to digital signatures, and this is not fully how digital signatures work. We have something missing here. In other words, this scheme, as you see here, does not provide any security properties. Well, why is that? Well, here, what is Alice doing? Alice received the signed message, right? And she applies Bob's public key on this. And because when you apply encryption twice with the public and private keys, you get the original message, right? This is the operation Alice is doing. But the problem is, I can just send garbage to Alice, some garbage message. Let's say now instead of KB minus of M, now Alice received garbage. And she thinks this is the message encrypted by Bob's private key. So what will she do? She will try to decrypt this message using Bob's public key, right? This is the operation she did here. This is the operation she did here. So she will do the same operation, thinking that this is the signed message by Bob. But you can decrypt anything. What you are decrypting doesn't have to be the ciphertext. You can decrypt anything. After all, decryption is just a function. So when you decrypt my garbage, you will have another garbage. Let's say garbage 2. And now should Alice think that this garbage 2 is coming from Bob? Was it clear? This is a bit complicated. I get it. So if you do not understand, I can repeat. Okay, you look confused. Let me repeat. All right, let's do it here. Okay, so let's go back to asymmetric key encryption first, okay? So we have Alice here, and we have Bob here. So Alice has Ka plus and Ka minus. This is her public key. This is her private key. And Bob has the same for himself. He has Kb plus as his public key, and he has Kb minus as his private key. So obviously Alice also knows Kb plus, just like everyone else, and Bob also knows Ka plus, just like everyone else. So if they want to provide confidentiality, so this is preventing any adversary, any attacker to read your messages, from reading your messages, right? In public key cryptography, what Alice is doing is that when she creates a message, she just encrypts that message using Bob's public key, sends that message to Bob, and because only Bob knows the private key that can decrypt this thing, he then applies Kb minus to that ciphertext, and he obtains the message. Now, this is confidentiality, and we learned this earlier today. Now, for integrity or message authentication, let me just show you what doesn't work. Okay, so now we are not encrypting the message with the Bob's public key, but we have to attach something of our own to prove that it is coming from us. So when Alice wants to digitally sign that message, she needs to attach something of her own. That is her private key. So, okay. So now, if she encrypts that message with her private key, Bob will receive this, and because Bob knows Alice's public key, just like everyone else, he will just compute this, and then he will see if this is equal to okay, this is not the scheme that works, this is the scheme that doesn't work, right? And then he will obtain M. This is what you just saw in the slide earlier, right? But this doesn't work because now anyone can send any garbage to Bob, just any bit sequence to Bob, claiming that this is a message encrypted with Alice's private key. So if I send, let's say I'm sending this from somewhere else, right? If I'm sending garbage with the claim that, this is in fact, my claim is that this is in fact some message encrypted with Alice's private key, well, Bob will then attempt the same operation, this operation, to my garbage, and that is, he will try to decrypt it using Alice's public key, and because this encryption or decryption operation is, after all, just a function, he will obtain something. And then he will be fooled into thinking that this is the message coming from Alice. So it doesn't work. Now, are we on the same page on this? Okay. All right. And that is why, in addition to this encrypted message, we have to attach the message itself. So this is how it actually works. Now, Alice, who is sending here? Okay, so in the example here, Bob was sending, but in my example, Alice was sending. Sorry about that. So here, Bob is sending a message to Alice, okay? And he is encrypting the message with his own private key, and with a message, he has to send the message along with the encrypted message. And now, Alice will apply Bob's public key to that encrypted message, and she will obtain something. And then she will compare if this is the same, and then this message has to be the same message Bob sent her. So this prevents me sending some garbage and claiming that this is in fact Alice's encrypted message. So Alice can now verify that. So these are the guarantees provided by this digital signature. Bob signed M. No one else could have signed M because only Bob knows KB minus Bob's private key. And it also guarantees that Bob signed M, but not some garbage, because Bob also sent this message. And when I decrypted the KB minus of M, I obtained that same message. So Bob did not sign some garbage message, but Bob indeed signed M. And there is one other property here called non-repudiation. Repudiation means denying something. So here, because Bob signed that message with his private key, he cannot later deny that he in fact signed that message. So this is just like the signatures we have in physical life. So once you sign something, some document, later you cannot deny that you signed it, because anyone can now bring your document with your signature to court and show the court that you in fact signed it, and that is a sufficient proof. So because we have asymmetric keys here and only Bob possesses his private key, once he signs a document with his private key, it is sufficient proof that it must be him, but only him, who signed the document. This property doesn't apply for symmetric key-based message authentication codes, because there we have shared keys, correct, between the senders and receivers. And if the receiver claims that, this sender sent me this message authentication code, so I can sue him for sending this maybe insult, let's say, the receiver can say, the claimed sender can say, no, I didn't send this. This is a shared key that we have. And using that shared symmetric key, my receiver forged that message authentication code herself, so I'm not liable. So this is different with digital signatures. Here, the sender cannot deny sending that message. Any questions? Okay, but in fact, even this is not enough. Even this is not secure. But I will not go through details as to why this is not secure. It's a little more complicated. But let me just show in practice how digital signatures work. So instead of signing the message directly, instead of encrypting the message directly with the private key, we instead take the hash of the message, compute a digest out of the message, and then we encrypt that digest with the private key. So this is the encryption protocol. We have a message, and we apply hash function on the message and obtain this digest. And we encrypt that digest using our private key. So what we compute is kb minus of h of m. So we are not computing just kb minus of m. No. We compute kb minus of h of m. If you're interested later, I can explain why we do so. But I think for the time being, it is just sufficient to know that this provides the integrity guarantee, but not just encrypting the message directly. Okay? And on the receiver side, Alice verifies the signature by doing these operations. So she received the message M, right? And she can compute the same hash of the message because hash functions are public. And then she applies, she also received this, right? The signature of that message. She applies then Bob's public key to that signature. And once I apply this, what happens? These cancel out, and I get h of m. And then I check whether this is equivalent to the digest of the message I received from Bob. So overall, what did Bob send? Bob sent the message itself and the signature of that message. Bob sent both. And Alice received both. All right? Here's just another example, a little more concrete. So this is the signing part, or the sender part. So let's say Bob has a very long message here. One other benefit of hashing is also to shorten the message length into a 256-bit size digest, and then encrypting that digest is easier than encrypting a long message. Because remember, public key cryptography is expensive. We don't want to encrypt using RSA very long messages, and encrypting the digest is easier. So here Bob has a very long message. He takes the hash of that message. Let's say this is the much shorter digest of that message. And then Bob encrypts that hash using his private key. And here is the signed hash. In other words, Bob's signature. So this is kb minus of h of m, also known as Bob's signature. And he sends this along with the message itself, this very long message itself, to Alice. And Alice receives them. So here is the message. She puts the message here, and she puts the signature here. Okay, and for the message, she just computes the hash. So she brings the hash or the digest value here, right? And for the signed hash, she runs the encryption algorithm using Bob's public key. In other words, this operation is kb plus of kb minus of h of m. And because encrypting consecutively with a asymmetric key pair gives out the message itself, this will also be h of m, and then you will see if these H of M's are the same. You compare, and if they are equal, you just accept the signature, and now you know that the message is coming from Bob and it has not been tampered with in transit. Any questions? Okay. So let's now compare the two integrity protection methods we have learned, namely the message authentication codes, which were using symmetric key cryptography, and the digital signatures, which were using asymmetric key cryptosystems. So the message authentication codes are lightweight because, quite frankly, the only operation we do here is the hashing operation. And hashing operation is a very simple operation. It is in the order of perhaps microseconds for today's computers. And this is good for unicast settings. Unicast meaning that it is for point-to-point communication. I only have one destination for my message. And if I have only one destination, I can share a secret with my destination, and I can compute the hash of my message, and then only my destination can verify that message. And I don't have to worry about sharing a group key with multiple people. But if I have a multicast communication setting or a broadcast communication setting where I have to share keys with multiple people, then any of these destinations can also forge a message on behalf of me and claim that the message is coming from me. So MAC is only good for unicast settings. For broadcast settings, it is not that preferable. But we use this in transport layer security, TLS. So it is very widely used in the web. And we also use it for some kind of link state routing protocol. So these routers, it's open shortest path first protocol. So these routers share their routing updates with each other using message authentication codes. And in comparison, well, we have digital signatures, which are more expensive because they have to use some public key encryption method like RSA. And if you are using RSA, you have to do modular exponentiation, which is much more expensive compared to hashing only. And good thing about them is that they are applicable to multicast or broadcast scenarios. When I have multiple destinations, I do not have to share a different key with each of them because all of them will possess my public key. Now they can verify my signature using my public key. I do not have to share key with all of them. I just share my public key once. And no party among my destinations can impersonate me because they do not share my private key with me. Only I know my private key. And only I can compute k minus of some hash. And not only my destinations, but anyone, such as the court, such as a judge in a court, can verify that this signature is coming from me. So all they need to do is to obtain my public key somewhere, and then they will be able to verify. If we recall what we had in the message authentication codes, for someone to be able to verify my MAC, my message authentication code, they need to possess the shared secret key, right? If I sent them H of M S, to be able to verify that, they have to possess my shared secret key. And one other property we discussed is the non-repudiation, that digital signatures cannot be denied. Once you sign something and once you give out that signature with the message to someone, they can claim later that you in fact signed this and you cannot deny signing this. And digital signatures are also used in TLS, and they are used in emails. Therefore, because this S in the HTTPS is the extension of TLS, they are also widely used in the web. And we're going to see how TLS works very briefly later on. Okay, but there is still one thing we haven't discussed with the digital signature. So we said that even if you do not share a secret, you can establish a shared secret using a scheme like RSA, correct? But even in the digital signatures, even in using RSA, you must ensure that your destination knows your public key. I always assumed that in my examples that our destination knows the public key. How to make sure that our destination knows our public key? One problem that can arise may be that if someone sends them the wrong public key, then they will perform the verification with the wrong key, and that could potentially lead them to accepting messages that are in fact not originating from us. And in the next class, we are going to see the method of securely establishing public keys at the destination. And for that, we use public key certification by certificate authorities. I think that's all for today's class. And remember to do the tutorial questions on multimedia chapter. I'm going to solve them next week. All right? Yeah, see you.